Okay, next, just talking about acid-base indicators. We typically use these indicators in titrations to tell when we have a change in pH. And the change in pH can let us know whether or not we're going from something acidic to something neutral, from something neutral to something basic, or from something acidic to basic, or vice versa. So I just want to point out one, you don't have to memorize the specific color changes, but I just wanted to show you here, we have phenolphthalein. This pH indicator is colorless if it's in an acidic or neutral solution, and is only going to change color if the solution becomes basic, at which point it would turn a pink shade. So like I said, we typically use acid-base indicators when you're doing titrations. So this is an example of a titration that's set up for you over here. When you're trying to do acid-base titrations, really you're trying to analyze a solution to help determine an unknown concentration. So when we're doing these, we always have a standard solution. And the standard solution is going to be the one with your known concentration. So this is your setup for a titration over here to the right. You have a flask down here. The flask is going to contain your unknown solution, and you're going to have your pH indicator in with it, such as phenolphthalein that we talked about before. This apparatus up here, this is your burette, and this is going to read the volume that's delivered. And what it's holding is your known solution with known volume and known concentration. And you're going to slowly deliver the solution that's in your burette into the flask until you have a color change. And once you have the color change, that means you've reached something called your endpoint, which tells you when one reactant has completely reacted with another reactant. So those terms are listed for you here, but the only thing I haven't talked about yet is a buffer. And a buffer is a solution that resists changes in pH when small amounts of strong acid or base are added. So again, we don't have a specific buffer for a strong acid or base because a buffer can act as either an acid or a base. So we do have a couple example problems for titration, and these are similar to the problems that you did at the end of chapter 13. So the first example, we have a 10 milliliter sample of acetic acid that requires 37.55 milliliters of 0.233 molar sodium hydroxide. What is the concentration of acetic acid? Notice they are giving you the information for one substance and asking for information for another substance. So this means that you actually need to start with a balanced equation because you're going to need the mole to mole ratio. So let's start writing it out. We have acetic acid. That's reacting with sodium hydroxide. We have an acid and we have a base, so you should know this is a neutralization reaction that is going to give you water. And a salt. The next thing you need to make sure after you have your equation is to make sure that it's balanced. So if I look here, everything is balanced, so we don't need to do anything else. And the next thing that we need to do is take the volume that we're given, and the volume that we're given is actually in milliliters. So what you first need to do is take the amount that you're given that's in milliliters and convert it to liters. So if we convert 10 milliliters to liters, I'm sorry, wrong one. This is the one we're working with first. We still need to convert it to liters. So if we take 37.55 milliliters and convert it to liters, you should get 0.0. So now we can take that volume and use our molarity. We can use molarity as a conversion unit. So if we look at our molarity, which was given as 0.233, what molarity is telling you is that you have 0.233 moles of sodium hydroxide per liter. Now we have what we're left with is moles of sodium hydroxide. Our goal is to get to moles of acetic acid, so we need to use our mole to mole ratio. If we look at our balanced equation, we have 1 mole of sodium hydroxide for every mole of acetic acid that we have. So if we plug all of this information into our calculator, what you should get is 8.75 times 10 to the negative third moles of acetic acid. The problem is the question is asking you for the concentration. So because it's asking you for the concentration, which is the same thing as molarity, we have to take the volume of the sample of acetic acid given, that's in milliliters, and convert it to liters. So if we take 10 milliliters and we convert it to liters, you should get 0.0100 liters, or 1 times 10 to the negative second liters of acetic acid. So then we're going to put that here. 1 times 10 to the negative second liters of acetic acid. And our final concentration should be equal to 8.75 times 10 to the negative 1. You can either write molarity, because concentration is expressed as molarity, or you could write moles per liter. That's up to you. Okay, so let's look at another titration example where we have 10 milliliter sample of 0.5 molar sulfuric acid is going to be titrated with 0.250 molar sodium hydroxide. What volume of sodium hydroxide is required for titration? So again, we are looking that we are given information for one substance and it's asking for information for another substance. So we need to start with a balanced equation because we're going to need the mole to mole ratio. So we're going to start writing out our balanced equation. Okay, I look at this equation and I can tell that it is not balanced because I have 1 sodium on the reactant side and 2 sodium on the product side. So you need to make sure after you write your balanced equation, after you write your chemical equation, that it is balanced. So I put 2 here, which then changes the number of oxygens and hydrogens I have. So then I'm going to put a 2 here. So now I have my balanced equation. So again, we're going to multiply our volume by the concentration, but we have to make sure our volume is in liters. So we have to take our 10 milliliters and convert it into liters, which we did previously. So we're going to start with our volume. And we're going to multiply it by our concentration, which is molarity for sulfuric acid, because that was the volume that we were given. So the volume that we were given Okay, what we have so far leaves us with moles of sulfuric acid, but we need to get to volume of sodium hydroxide. So we need to use our mole to mole ratio. In this case, we have 1 mole of sulfuric acid for every 2 moles of sodium hydroxide. Now we're left with moles of sodium hydroxide. So now we need to use the concentration in order to get the volume that remains. So the concentration, again, is the same thing as molarity, which we are given. But you want to make sure you represent it in a way that you can cancel out your units. So we're going to write 0.250 moles of sodium hydroxide for every 1 liter of sodium hydroxide that we have. So again, you're using molarity as a conversion factor, which means you can arrange its components however you want to arrange it. If we plug this into a calculator, you should get 0.0400 liters of sodium hydroxide. And you can also write this as 4.00 times 10 to the negative second liters of sodium hydroxide. Okay, so I encourage you to press pause and then see if you can work this problem out on your own, and then come back and we'll do it together. Okay, so the first thing, again, we're given information for one substance and we're asking for information for another. So the first thing that you need to do is write your chemical equation and make sure that it's balanced. So that should be what your balanced equation looks like. The next thing that we're going to do is look at the volume of the sample of the information that we're given for. So we're given 25 milliliter sample of 0.5 molar phosphoric acid. So we're going to start with what we're given the most information for, which is phosphoric acid. The volume is given to us in milliliters, so we have to convert this to liters. So if we convert 25 milliliters into liters, we get 0.025 liters, and we're going to start with the volume that we're given. We're also given the molarity for phosphoric acid, which we're going to use to find the moles of phosphoric acid. So again, we can use molarity as a conversion factor, where we have 0.0500 moles of phosphoric acid per liter of phosphoric acid. So what we're left with as represented here is moles of phosphoric acid, but our goal is to get to volume of barium hydroxide. So now we need to convert this using our mole to mole ratio into moles of barium hydroxide. So we need our balanced equation. So for every 2 moles of phosphoric acid that we have 3 moles of barium hydroxide. Okay, so now we've converted our original volume into moles of barium hydroxide, but our goal is to get to volume of barium hydroxide, which means we need to utilize the molarity or the concentration that was given to us for barium hydroxide. So molarity is a conversion factor, so we can write the number of moles at the bottom so that this can cancel out. Per liter. And if you take all of this information and you plug it into your calculator, you should get 0.8 liters of barium hydroxide. We have one more example, and again, I encourage you to push pause and try to work this problem on your own, and then come back to see if you were able to complete it and got everything correct. Okay, so reading this problem, you're given information for one substance and you're asking for information for another substance, which means that we need to write a balanced equation because we're going to have to do a mole-to-mole comparison. So the first thing you should have done was write the balanced equation. Okay, there's the chemical equation. I'm looking at it and it is balanced, so you don't need to do anything further. You're going to start with the volume of the substance that you're given the most information for, which is lithium hydroxide, because you're given both the volume and the molarity. Our volume is given to us in milliliters. We can't use milliliters. We need to convert it to liters because that is the units for molarity or concentration. So we take 25 milliliters and convert it into liters, and you should get 0.025 liters. And that's what we're going to start with. Liters of lithium hydroxide. Okay, the next thing we need to use is our molarity, which is our concentration, which is a conversion factor. We need to make sure we write molarity in a way that we can cancel out our units. So we put liter at the bottom for every 2.50 moles of lithium hydroxide. So now what we're left with as represented here is moles of lithium hydroxide, but our goal is to get the concentration of nitric acid. So this is where we're going to need our mole to mole ratio, and we're going to get this from our balanced equation. So for every 1 mole of lithium hydroxide we also get 1 mole of nitric acid. So now we're left with moles of nitric acid. And we can use this to determine our concentration. So if you plug all of this information into your calculator, you should get 6.3 times 10 to the negative third moles of nitric acid. So this is moles, but what it's asking us for is the concentration or the molarity of nitric acid. So concentration and molarity are the same thing. So molarity or concentration is represented as moles per liter. You are given the volume in milliliters. We have to convert this to liters to get the true units for concentration, which is 1.0 times 10 to the negative second liters. So we take this, we divide our moles by our liters so we can get the true concentration.